Rayon represents one of the earliest and most successful examples of sustainable polymer engineering. Unlike petroleum-derived synthetic fibers, such as polyester or nylon, rayon is manufactured from naturally occurring cellulose through a regeneration process in which cellulose is dissolved, chemically processed, and subsequently reformed into continuous fibers. Because the polymer backbone remains cellulose, while the supramolecular structure is reconstructed, rayon is generally classified as a regenerated cellulose fiber rather than a synthetic polymer. Today, regenerated cellulose fibers occupy an important position between natural fibers and synthetic polymers. They combine the comfort, moisture absorption, and biodegradability of natural cellulose with the processability and control of properties associated with man-made fibers. Modern regenerated cellulose fibers include Viscose Rayon, Modal, Lyocell, and Cupro, each produced through distinct dissolution and regeneration routes that yield unique structural characteristics and performance properties. Growing environmental concerns surrounding petroleum-based textiles have renewed scientific interest in regenerated cellulose fibers, particularly newer technologies such as Lyocell that significantly reduce solvent emissions while maintaining excellent mechanical performance. Historical development of rayon. The invention of rayon emerged during the late 19th century in response to the increasing demand for an inexpensive alternative to natural silk. At that time, silk production was limited by the availability of silkworm cocoons, making silk one of the most expensive textile fibers. The earliest attempts to produce artificial silk were made by the French scientist Hilaire de Chardonnay, who developed nitrocellulose fibers in the 1880s. Although these fibers possessed a silk-like appearance, they were highly flammable and unsuitable for widespread commercial use. A breakthrough occurred in 1892, when British chemists Charles Frederick Cross, Edward John Bevan, and Clayton Beadle patented the viscose process. Their technology transformed cellulose into a soluble intermediate known as cellulose xanthate before regenerating pure cellulose fibers through wet spinning. Commercial production expanded rapidly during the early 20th century, establishing rayon as the world's first commercially successful semi-synthetic textile fiber. Initially promoted as artificial silk, rayon eventually evolved into a diverse family of regenerated cellulose fibers. Continuous improvements in fiber chemistry and spinning technology led to the development of high-wet modulus, HWM, rayon, modal fibers, Lyocell, and Cupro, each addressing specific shortcomings of conventional viscose rayon. Cellulose regeneration, from cellulose 1 to cellulose 2. Natural cellulose consists of linear beta-1, 4 linked D-glucose chains that assemble into highly ordered microfibrils through extensive intermolecular hydrogen bonding. Native cellulose found in cotton and wood is referred to as cellulose 1, characterized by high crystallinity and parallel chain orientation. The manufacture of rayon fundamentally alters this crystalline organization. During dissolution, the native hydrogen bonding network is disrupted, allowing individual cellulose chains to separate. Upon regeneration, these chains recrystallize into cellulose 2, a thermodynamically more stable polymorph with antiparallel chain arrangement. Although the chemical composition of cellulose remains unchanged, the transformation from cellulose 1 to cellulose 2 modifies several structural features: crystallinity, molecular orientation, degree of polymerization, hydrogen bonding network, amorphous fraction. These structural changes largely determine the softness, moisture absorption, dyeability, dimensional stability, and mechanical properties of regenerated cellulose fibers. General manufacturing of regenerated cellulose fibers. All regenerated cellulose fibers are produced through four fundamental steps: purification of cellulose from wood pulp or cotton linters, dissolution using an appropriate solvent system, extrusion through spinnerets, regeneration of cellulose into continuous fibers. Wet spinning is the dominant manufacturing technique. The cellulose solution, spinning dope, is extruded into a coagulation bath where cellulose precipitates, forming continuous filaments that are washed, stretched, dried, and finished. The choice of solvent system distinguishes the various Rayon technologies and largely determines fiber structure, manufacturing cost, environmental footprint, and final performance. Types of Rayon. Viscose Rayon. Viscose rayon remains the most widely produced regenerated cellulose fiber worldwide because of its relatively low manufacturing cost and excellent textile versatility. The process begins by treating purified cellulose with sodium hydroxide to produce alkali cellulose. Controlled aging reduces the molecular weight to improve processability. The alkali cellulose subsequently reacts with carbon disulfide, CS2, to form cellulose xanthate, which dissolves in dilute sodium hydroxide to produce the characteristic viscous orange solution known as viscose. The viscose solution is filtered, degassed, and extruded through spinnerets into sulfuric acid, where cellulose is regenerated and the xanthate groups are removed. The resulting fibers undergo washing, bleaching, stretching, and finishing. Viscose rayon exhibits excellent softness, high moisture regain, outstanding dyeability, silk-like drape, relatively low wet strength. Despite these advantages, viscose production has been criticized because carbon disulfide is a neurotoxic solvent, and conventional manufacturing consumes large quantities of chemicals, water, and energy. Modern facilities have improved sustainability through solvent recovery systems and wastewater treatment, although environmental concerns remain. Modal. Modal is an advanced high-wet modulus, rayon developed to improve the mechanical limitations of conventional viscose. Manufacturing follows a modified viscose process, but uses carefully selected beechwood pulp with optimized polymerization and spinning conditions to produce fibers possessing greater molecular orientation and crystallinity. Compared with conventional viscose, Modal exhibits higher tensile strength, superior wet strength, greater dimensional stability, excellent resistance to shrinkage, enhanced softness, improved durability after repeated laundering. These characteristics have made Modal particularly attractive for premium apparel, sportswear, underwear, and luxury home textiles. Because Modal production generally employs improved chemical recovery technologies and sustainably managed beech forests, its environmental footprint is somewhat lower than conventional viscose. Lyocell. Lyocell represents the most significant technological advancement in regenerated cellulose fiber manufacturing. Unlike viscose, Lyocell avoids chemical derivatization of cellulose entirely. Instead, purified cellulose dissolves directly in N-methylmorpholine N-oxide, NMMO, forming a homogeneous spinning solution without producing cellulose xanthate. The cellulose solution is extruded into water, where cellulose regenerates through solvent exchange rather than chemical decomposition. A defining advantage of the Lyocell process is its closed-loop solvent recovery system, in which more than 99% of NMMO is recovered and recycled. Consequently, Lyocell production generates substantially lower emissions than the viscose process. Lyocell fibers possess the highest tensile strength among regenerated cellulose fibers, excellent wet strength, superior moisture management, smooth fiber surfaces, excellent dimensional stability, biodegradability, outstanding durability. Commercially known under trade names such as Tencel, Lyocell has become increasingly popular in premium apparel, medical textiles, technical fabrics, and sustainable fashion. Cupro, Cuprammonium Rayon. Cupro is produced primarily from cotton linters, a byproduct of cotton processing. In this process, cellulose dissolves in Schweizer's reagent, a copper ammonia complex, Cuprammonium hydroxide. Following dissolution, the solution is extruded into an acidic coagulation bath, where cellulose regenerates into fine, continuous filaments. Cupro fibers are distinguished by exceptional softness, silk-like luster, smooth surface, excellent drape, high moisture absorption, hypoallergenic characteristics. Because Cupro production involves copper-containing chemicals and ammonia, modern manufacturing facilities employ solvent recovery technologies to minimize environmental impacts. Cupro is primarily used in luxury garment linings, high-end fashion fabrics, and premium textiles requiring exceptional comfort. Comparison of major rayon fibers. Although all rayon fibers are regenerated cellulose materials, differences in their manufacturing processes produce distinct microstructures and performance characteristics that determine their suitability for specific textile applications. Viscose rayon is the oldest and most widely produced regenerated cellulose fiber. Manufactured using the sodium hydroxide carbon disulfide viscose process, it is valued for its exceptional softness, silk-like drape, high moisture absorbency, and excellent dye ability. However, its relatively low wet strength and dimensional stability limit its durability during repeated laundering. Furthermore, the viscose process is the most chemically intensive among rayon manufacturing methods, requiring careful recovery of carbon disulfide and extensive wastewater treatment to reduce environmental impacts. Modal is an improved form of viscose rayon that is produced using modified processing conditions and high-quality beechwood pulp. Compared with conventional viscose, Modal possesses greater molecular orientation and higher crystallinity, resulting in significantly improved tensile strength, particularly under wet conditions. It is more resistant to shrinkage, retains its softness after repeated washing, and offers excellent moisture management. These advantages make Modal particularly suitable for premium apparel, activewear, underwear, and luxury home textiles. Modern Modal manufacturing also incorporates improved chemical recovery systems, reducing its environmental footprint compared with conventional viscose. Lyocell represents the most technologically advanced and environmentally sustainable member of the rayon family. Unlike viscose and Modal, cellulose is dissolved directly in N-methylmorpholine N-oxide, NMMO, without chemical derivatization, eliminating the need for carbon disulfide. The nearly closed-loop manufacturing process enables recovery and recycling of more than 99% of the solvent, greatly reducing emissions and waste generation. Structurally, Lyocell fibers possess a highly uniform and compact morphology, giving them the highest tensile strength and wet strength among regenerated cellulose fibers. They also exhibit outstanding moisture management, dimensional stability, durability, and biodegradability, making them ideal for high-performance apparel, technical textiles, and medical applications. Commercially, Lyocell is best known under the Tencel trademark brand. Cupro, Cuprammonium Rayon, is produced from purified cotton linters dissolved in a copper ammonia complex known as Schweizer's reagent. The resulting fibers are exceptionally fine, smooth, and lustrous, closely resembling natural silk in appearance and feel. Cupro exhibits excellent drape, high moisture absorption, and hypoallergenic properties, making it highly desirable for luxury garment linings, premium fashion fabrics, and specialized textile applications. Although the production process requires careful management of copper containing chemicals and ammonia, modern manufacturing facilities employ solvent recovery and recycling systems to improve sustainability. Overall, the progression from Viscose to Modal, Lyocell, and Cupro illustrates the continuous evolution of regenerated cellulose technology toward improved fiber performance and more sustainable manufacturing. Viscose remains the most economical and widely available rayon due to its low production cost, whereas Modal offers enhanced durability and laundering performance. Lyocell has become the benchmark for environmentally responsible regenerated cellulose production, combining superior mechanical properties with a low environmental footprint. Cupro, while manufactured on a smaller scale, occupies a specialized niche in the luxury textile market because of its silk-like aesthetics, softness, and exceptional drape. Together, these regenerated cellulose fibers provide manufacturers with a versatile portfolio of materials that bridge the gap between natural fibers and synthetic polymers, supporting applications ranging from everyday clothing to advanced medical and technical textiles. Impact on the fiber and textile industry. The development of rayon fundamentally transformed the textile industry by providing a cost-effective alternative to silk, while retaining many desirable aesthetic properties. Throughout the 20th century, viscose rayon became one of the world's most important textile fibers due to its affordability, comfort, and versatility. Subsequent innovations expanded the performance envelope of regenerated cellulose fibers. Modal improved durability and laundering resistance, making regenerated cellulose more suitable for everyday garments. Lyocell introduced environmentally responsible manufacturing while simultaneously achieving superior mechanical properties, establishing itself as one of the leading sustainable textile fibers. Cupro, although produced in smaller quantities, continues to occupy a niche market in luxury fashion because of its remarkable softness and drape. Beyond apparel, regenerated cellulose fibers have found applications in non-woven hygiene products, filtration media, medical textiles, wound dressings, engineered composites, and biodegradable packaging. Their excellent moisture management, biocompatibility, and biodegradability make them attractive alternatives to petroleum-derived fibers in numerous advanced applications. The increasing demand for sustainable textiles is expected to accelerate the adoption of regenerated cellulose fibers, particularly Lyocell, as governments and manufacturers seek lower-carbon, biodegradable materials. Advances in green solvent systems, closed-loop processing, enzymatic cellulose dissolution, and biomass valorization are likely to further improve manufacturing efficiency while reducing environmental impacts. In conclusion, rayon represents one of the earliest successes in polymer engineering and remains an indispensable class of regenerated cellulose fibers. By converting native cellulose 1 into regenerated cellulose 2, manufacturers have produced fibers that combine the renewability of natural cellulose with the tunable properties of engineered materials. Conventional viscose rayon continues to dominate global production due to its low cost and desirable textile properties, whereas Modal offers enhanced durability and dimensional stability. Lyocell has emerged as the benchmark for sustainable regenerated cellulose manufacturing because of its closed-loop NMMO process and superior mechanical performance, while Cupro provides premium silk-like aesthetics for luxury applications. Collectively, these fibers have significantly influenced the global textile industry by providing biodegradable, comfortable, and high-performance alternatives to both natural and petroleum-based fibers. Continued advances in green chemistry, solvent recovery, and cellulose processing are expected to further strengthen the role of regenerated cellulose fibers in the transition toward a more sustainable and circular textile economy.